Hypothesis test with larger samples, example 8. You flip a coin 20 times, n equal 20 times, and the coin turns up x equal 11 times. Does this sample provide sufficient evidence that the coin is unevenly weighted? Okay, so let's make a diagram again showing the relationship between the sample and the population. So we're using information from the sample to make predictions about the population. So we have a sample of n equal 20 tosses. There were the proportion of heads represented by p hat be 11 over 20, which is a decimal 0.55. Okay. And this is a sample from a larger population. The population of all possible tosses of the coin, and of all possible tosses. The proportion of heads in the long run represented by the letter P, and we don't know what that is. Our best estimate is based on the sample proportion of 55%, but the samples will vary from one sample to another. So if we did another sample, maybe it's only 47%. Anyway, our sample proportion is an estimate for the unknown population proportion, and we want to compare it to if the coin is evenly weighted, the proportion of heads in the long run represented by P0, that should be 1 over 2, or 0.5. Because if the coin is evenly weighted, it should turn up heads half the time and tails half the time. Okay, so we have the head. Here we have a quarter. We have the head here, George Washington, and then the tail. Looks like an eagle. So if it's evenly weighted, it should turn up heads and tails equally often. That time it turned up a tail. Okay, so let's state the hypotheses more formally. So with 95% confidence and 5% doubt, we want to test H0 or H0, P equal 0.5, the coin is evenly weighted, versus HA, P is not equal to 0.5, coin is not evenly weighted. So this is a two-sided test. We're using not equal to in the alternative because if there are if in the long run the proportion of heads is more than 1/2, it'll be unevenly weighted. But also if the proportion of heads in the long run is less than 1/2, the coin is unevenly weighted. So that's a two-sided alternative. And the confidence level is set by the researcher. 95% is a fairly common one that we'll usually be using. Some researchers researchers use 99% confidence and 1% doubt, but we'll usually use the 95% confidence and 5% doubt. Okay, so the first step in testing these hypotheses would be to check whether we can use the z-score and the z-table. So we want to check to see whether n times p0 is at least 5 and n times 1 minus p0 is at least 5. So a sample size n is 20, p0, that's the value of p if h naught is true, is 0.5, 10 times 0.5 is 10, and that is greater than or equal to 5. Okay. And then we also want to check whether n times 1 minus p0 is at least 5. 1 minus 0.5 is 0.5. So 10 times 0.5 is 10, greater than or equal to 5, and that's a yes. So we got 2 yeses there. So that means we can use the z-score and the z-table. This should be a p0 here. The next step is to compute the mean or expected value of x. X is the number of heads, and on the average we could expect n times p0, so that's going to be 20 times 0.5 or 10 heads. So on the average we would expect 10 heads. And then standard deviation of x is given by this formula here, square root of n times p0 times 1 minus p0. So the square root of 20 times 0.5, and 1 minus 0.5 is also 0.5. And we can put that in the calculator. Second square root 20, whoops, let me turn on here. Second square root 20 times 0.5 times 0.5, and equals, get 2.236 something. Okay, 2.236067977, and just so I don't have to type this in again, I'll store it in my calculator. Then I can recall that later. Okay, so we have the mean and standard deviation, and we know what x is. X is was 11 tosses, 11 heads, rather. Okay, so we can compute the z-score. The same formula that we were using earlier in the semester. Score minus the mean divided by the standard deviation. So this is going to be 11 heads minus the mean is 10, divided by the standard deviation is 2.236067977. Okay, so we do 11 minus 10, and then we want to push equals, because subtraction comes before a division bar that goes all the way across, and then divided by second recall equals approximately 0.45. 0.45. Okay, so this is not an unusual z-score. Anything between -2 and 2 would be not unusual. We learned that earlier in the semester with the empirical rule and also Triola's range rule of thumb, that most of these scores are between -2 and 2, and anything beyond that would be unusual. More precise numbers would be -1.96 and positive 1.96. And this is assuming 95%, that we want 95% confidence. So 0.45 is between -1.96 and positive 1.96. So we fail to reject H naught. the sample does not provide enough evidence to say that the coin is unevenly weighted. Okay, we could also do steps 2, 3, and 4 all at once, rather than to break it down there. If we step 2 was to compute the mean, and step 3 was the standard deviation. Step 4 was the z-score, but we can do it all in one shot. The z is x minus n times p0 divided by the square root of n times p0 times 1 minus p0. So it's going to be 11 minus 10 divided by square root 20 times 0.5 times 0.5. 1 minus 0.5 is 0.5. And so then the subtraction comes before a division bar that goes all the way across. So you want to push equals after you put in the subtraction. 11 minus 10 and then equals. And then divided by second square root. And this will be 20 times 0.5 times 0.5 equals. And it's the same number we had before, approximately 0.45. So not an unusual z-score, does not provide strong evidence. Okay, so some of the exercises will ask you to do an additional step, which is to use the z-table to get a p-value. A p-value is the probability of getting a result this extreme if h0 is true. So we want the probability that z is either greater than 0.45 or z is less than negative 0.45. So this is a two-sided test. So we want to include both extremes, because a coin is unevenly weighted if there's either more heads than tails or fewer heads than tails. So the picture looks something like this, and the shaded area represents the probability of getting a result that extreme. So I want the probability that z is either greater than a positive 0.45 or less than a negative 0.45. Well, so this is a two-tailed test, but our z-table, the one that we're using anyway, is only has a left tail in it. So we can, in order to compute the p-value using our table, we need to use the left tail and multiply by 2. So this is 2 times the probability z is less than negative 0.45. So this is I'll draw the picture again. And here we want just the left side here. So we want to look in row negative 0.4 and column 5 of the z-table. And so row negative 0.4 and column 5, and we get a z-score of 3264, and we have to then multiply that by 2. So this is going to be 2 times, the p-value is 2 times 0.3264, and that's equal to 0.6528. So that's our p-value. P-value is 0.6528. And if we look at our chart here for interpreting the p-value, 0.6 is between 0.1 and 1, so that means the sample provides little evidence that the let's make myself more room here. sample provides little evidence that the coin is unevenly weighted. It might be that a bigger sample would provide stronger evidence, maybe, or it might not, but provides little or no evidence that the coin is unevenly weighted. So we're not going to, we don't necessarily, we're not, so this, basically we don't know. We're not accepting H naught, we're not rejecting H naught. Now if we had a bigger p-value, then we might reject H naught, but with this p-value that we have, I mean if we have a smaller p-value, a bigger z-value, but a smaller p-value, we might reject H naught, but we're never going to accept H naught, or at least if you want to be careful about your language, you never accept H naught, because it might be that a bigger sample would provide stronger evidence that the coin was unevenly weighted. Even if it's just a little bit unevenly weighted, maybe just a slight proportion of bigger chance of heads and tails, is still going to be unevenly weighted. And that concludes this presentation.